Okay, hi everybody. Thank you very much, organizers, for inviting me. It's really nice to be here. So this is joint work with Svetlana Shirokovskikh and Misha Skopenkov. Today I found out it's Misha's birthday. He's not here, but it's being recorded. Happy birthday, Misha. Okay, so I will tell you something about the usual electrical networks, and then I'll tell you some kind of new version of the story. Okay, so that's the plan. So let's say we have a graph which has n vertices, and we'll just number them. And we'll distinguish some part of them, and we will call them boundary. And the rest we will call internal. And a good way to visualize it is that you will have some kind of electrical network. It will have some boundary vertices on the boundary, and maybe some extra vertices inside, and there are edges connecting them. But it doesn't have to be this way. You make vertical boundary or internal just the force of your will. It doesn't have to be located in any way. So now each edge connecting two vertices K and L has conductance, some number associated to it. Let's say positive real number. It's called conductance. And we'll denote it CKL. And then our definition of electrical current will be like this. So electrical current is just an assignment of numbers UK to vertices, to all of them, and those are called voltages. And also numbers IKL to edges. And they're called currents. So that the following two properties hold. So that first property, I'm actually not sure why we didn't note it C. It's Ohm's law. Ohm's law. It says that IKL will be just conductance times difference of potentials. Okay, that's Ohm's law. And second law, my notes say KL. I'll stick to that. My notes say KL.
Yeah, IKL is minus ILK.
That's true. This is implied by this law. Yeah, I mean this is So you need to, but this is already included in Ohm's law, right? Yeah. Okay.
Complaining about sign. Imagine positron currents, not electron.
Okay, and second one, still not sure why it's I. It's Kirchhoff's law. I just took it from our paper, Kirchhoff's law, which says that for any boundary vertex, which means for k bigger than m, right, in our terminology, sum of all currents, not boundary, sorry, internal, for any internal vertex, right? So for any internal vertex, sum of all currents along all edges out of it is 0. N, I, K, L is 0. Okay, that's it. That's the definition of electrical current. And the way to think about it, the way we will play this game usually is that we consider potentials at the boundary vertices as given, right? Somebody tells us the conductances, and somebody tells us voltages at the boundary, and then everything else comes from it. So consider U1 through UM as given. And we consider UK for K bigism and for internal K and all the currents KL as unknown. Okay. And the theorem, I mean the very fundamental theorem, is that this uniquely defines the current. The linear system, this is just a linear system of equations. It has always unique solutions. This linear system has unique solution. And I'll show you an example in a second of all of this, but one more important definition before that. So we play this game again. We put some voltages in the boundary. We let the nature take its course according to those two laws, and this will create some potentials in its internal vertex, and it will create some currents on edges. And one thing, so imagine that somehow all inside the circle is black box, but we can measure things on the boundary. So one thing we could measure is through each of those boundary vertices, we could measure the current which results through this vertex to the outside world. So this is for any boundary vertex J between 1 and M, let's denote Ij to be the sum over all k's ijk. And we will call it incoming current. This is something you can actually physically measure in such a such a network. You can measure, you put certain voltages, and you can measure how much current flows through each of those boundary vertices. And it turns out that this map, right, so there are M inputs and M outputs, right? If you treat everything inside as a black box, your input is what voltages you plant at the boundary vertices, and then you can measure M numbers out of that, which are currents through those M boundary vertices. So this is map from vector U1 through UM into vector I1 through IM. It turns out to be linear. This is just multiplication by some matrix. It's a linear map. And the matrix which realizes it is called the response matrix. Right, so this linear map is just multiplication by some matrix which is associated to this specific graph with those specific conductances. Right, so to each such electrical network, there's associated response matrix. Okay, let's do an example. Let's say my graph looks like this. My vertex is 1, 2, 3, 4. 1, 2, 3 are boundary. Four is internal. There are some conductances on this thing. Maybe. So we are told number C14 over here, C24, C34. And we also plant some voltages, U1, U2, U3 at the boundary. And we are asking what does the voltage have to be in the middle, and also what should those currents be like. Let's pick direction. Let's call this I34. This one we will call I41, and this one I42. Okay, so this is a setup. I know what my conductances are. I plant some voltages here. And I want to know how it will behave. What will be this number? What will be those three numbers? Etc. So I honestly went to Maple. This is ancient software made in Canada. So I solved the system. And it told me, so it's enough to find U4. Everything else follows from it. So once I solved it, it told me that U4 will be equal to the C14, C24, C34, U3 divided by C14 plus C24, C34. Okay, and once so it turns out that basically laws of nature over there will force the voltage in the middle to be this kind of average voltage on the boundary. And then from this you can find all the currents and all the incoming currents, etc. So this one you just do C34 times U3 minus U4. You know everything here, so you can just, you could simplify now, find I34, etc. So that's just a regular story for how electrical networks work out. Any questions so far? And slightly more interesting is what is the response matrix in this case? Right, so again, it's a linear map which takes vector U1, U2, U3 to the vector which is, I guess in this case, it's still just those three currents over there. Right? So once you measure through the boundary points. So I will draw for you for the response matrix in this case. So what is the response matrix in this case? Turns out it looks like this, which we could, if we finish the computation over there, if I wrote down carefully what those I34 are, we could just see it. But so to summarize, so the matrix looks like this: 1 over C14 plus C24 plus C34, and then times something like this: 24 plus C34, C14, C24. It has to be a symmetric matrix. C14, C24, C24, C34. And the sum of all rows or sum of all columns in it will always be 0 vector. So C34. And the last one minus C14, 4 minus C24, C34, C34. C24. Right. So the idea somehow is that this matrix captures the electrical properties of the electrical network inside. If it's really a black box and you were to replace this network with some other network which has the same response matrix, then by measuring things outside, in the outside world without looking inside this box, you would never be able to tell the difference. Right? So somehow this matrix is supposed to capture as much information as there is about what's inside there. Okay. So far, so good? And then, of course, you could ask about, for example, what are the entries of this matrix? Is there a way to just write directly formula for them? So let me tell you a couple of theorems which go back, I guess, to Kirchhoff about 100 years ago, and to Kenyon and Wilson, much more recently, a more general version. Okay, so here's a theorem by Kirchhoff, which tells us how to interpret the single entries we see here. So of course, in this case, those entries look not super complicated, but for bigger graphs, they would look slightly more complicated. Question is, what are they? The entry in row I and column J will have the following formula. This is for I not equal to J. The entry Cij will be given as minus And then there will sum over some things in the denominator, where we take weight of those things, and sum over some things in the numerator, where we take weight of those things. And then the sum is over forests H such that each connected component of this forest has exactly one boundary vertex. Each component has one boundary vertex. And it's also, so that's the denominator, and the numerator is sum over G, such that the only difference from those h's is that I and G have to be now in the same component, and all other boundary vertices have to be in different ones. So such that I and J are two boundary vertices, are in the same component of G. So still forests, I and J have to be now in the same component, but all other boundary vertices still should have their own separate component of G. So let's see how it works in this example. So first of all, this denominator over here, that better be this thing over here, right? So we want to sum over all subgraphs of this graph. Well, I was told you can, well, somebody cannot see over here. I guess I will draw it here. So you want to take the sum over all subgraphs of this graph such that it's a forest, right? So forest is a cyclic graph. It will have some connected components, and we want to one-to-one matching, basically. So each connected component should have exactly one of the boundary vertices. So in this case, there are three ways to do it, right? We can take this edge, that's one component, this vertex, that's another, this vertex, that's another. This gives us, I guess, C1, 4. And there's two more choices which give us the other two terms. So you sum over them, you get this denominator. Yes? And if you want to get numerator, for example, let's take row 1, column 2, right? So we'll take the first row, second column. What is the meaning of this numerator? Well, now we need to take, again, a forest on this graph, such that 1 and 2 lie in the same connected component, but all other boundary vertices lie in different connected components. There's only one way to do it. Wait, is this how I numbered them? No, okay. Not this one. This, all right? Okay. Okay, so, and this would give us this way, it's C14, C24, and there's no summation because there's only one way to do it, right? So, okay, so that's a very classical theorem about, I teach it in my graph theory class. So how are some forests and trees and things like that related to electrical networks? And let me tell you just, so there is a vast generalization of it, as I said, by Kenyon and Wilson, the theory of groves, etc. But let me give you one more sort of example of theorem from this area. Also, I think that this still goes back to for a while ago. So what if we wanted to know something not about just single entries of response matrix, but about its determinant? Can anybody guess what is the determinant of response matrix? 0, correct. So determinant of response matrix is, of course, 0. As I told you, rows and columns add up to 0. But if you cross out nth row and nth columns, then it becomes not 0. It becomes something interesting. So here's a formula for the determinant of the result. Let's see how much time. So theorem continued. Determinant of So let's call response matrix C, and by C tilde I will mean C with the last row and last column crossed out. So determinant of C tilde is again something which looks like this. It's a sum of some animals H, weight of H, sum over some animals T, weight of T. H turns out to be the same animals as before, and T's sum over T's, which are spanning trees of our graph. Right, so somehow now all the boundary vertices have to be in the same component, so we have a spanning tree. Okay, now I will start telling you about a generalization of this story. Right? So we will talk about superport networks. And I will very soon come to where this idea of this generalization comes from. Just wait a little bit. So superport networks setup is very similar. So we have, the only difference is that boundary vertices one through m are partitioned into some subsets. So it's just not, right? So just some grouped into some subsets, partitioned into subsets A1 through AP. And let's pick in each subset one distinguished vertex and call it a root. AI has root Ri. And then the equations we impose, first of all, we still have the old Ohm's law and Kirchhoff's law, those don't change. So we have Ohm's law, we have Kirchhoff's law, just like I wrote them before. But we have this additional condition, which is called superport isolation. So those AIs will be superports. And the condition superport isolation says the following: superport isolation. It says that if we sum over all vertices in a particular superport, the incoming current into this vertex, which remember itself is a sum N, KL. Right, so this was incoming current into this particular boundary vertex. Now we lumped some of those boundary vertices together into a superport, and we're saying that sum of incoming currents has to be 0. Okay. So normally in an electrical network, we expect that overall incoming current to the whole thing to be 0 because it has nowhere to go. But here we require that additionally through each of those chunks, the incoming current has to be 0. Okay, so this is the condition, and also just in terms of how we set up the problem. So the next one is just, previously I told you that we will know the potentials on the boundary, and it will tell us everything else. Everything else will be forced or not. So what's the analog of this here? We will tell the system the boundary conditions as follows. If K is boundary vertex, oh, sorry, I think people cannot see, oh, camera cannot see. So I'll keep writing here. Oh, maybe. If K K is boundary vertex, and L is the root of that particular superport, right? So each boundary vertex lies in some lump of those boundary vertices. Each of them has a root. And what I will tell you the difference of potentials. The potential at K minus potential at L will be a given number delta KL. So this is a given number. So instead of telling you a potential at each boundary vertex, I'm telling you the difference of potentials within each superport. Right? So if you know difference between the root and any vertex, then you know difference between any two vertices. Somebody had a question?
Are these networks planar? You never assumed that, right?
So far, I don't assume anything like that. Yeah. OK, any other questions? So this looks a little bit strange because that's not what we were doing before, but it actually kind of is what we were doing before. So before, in just the usual setup, I said that we know the potentials at the boundary and tells us everything. But if you subtracted the same number from all the boundary potentials, it wouldn't change anything. We would still get the same currents. So in some sense, you can think that in the usual case, you also don't know the potentials, you just don't know the differences between them. So that's what we are doing here, but we know the differences within each superport. And OK, very soon I'll show you some slightly generic example. But before that, let's talk about very special examples. So here's one very special case of all of this. What if all boundary vertices lie in a single superport? This is just a regular electrical network, right? So the very special case number one. Example, only one superport. That's a usual electrical network. That's the first story I told you today. Usual case.
Even more special cases where everybody's in their own.
So, say it again?
Even more special cases when everybody's in their own.
That's right. I will mention that. So that's very. But OK, so let's. There's another interesting case. When all superports have size 2, right? So all boundary vertices come in pairs. And for each pair, you know that current going in through this one should be equal current going out through that one. Can anybody guess what's special about this case?
Is the graph disconnected, maybe?
Graph disconnected? No. The graph is the same. You can group those boundary vertices whatever what you want. Not sure what you mean.
But maybe if you have some edges where you have no current, you can remove them and just disconnect. Maybe not.
Maybe. No. But what I was trying to say that this is a so-called real life. Okay. So what do I mean by that? So it turns out that if you talk to electrical engineers, and most networks in real life are like that rather than like what I told you before. For example, when you plug in something into the wall, it has two things you plug in, right? So everything which comes through one thing leaves through the other one. Or if you stick a USB drive into your computer, there's actually also two things. There's everything which comes through one of them to USB drive leaves through the other. So if you talk to actual, I didn't do it, but my co-authors did. So apparently electrical engineers would tell you that real life is more like this than more like what we've studied before. So that's, I guess, the main motivation for looking at this kind. And of course, so there was no such thing as superport network anywhere. So what electrical engineers talk about is this special case when they come in pairs, and they call multiport networks. And then we realized that there's no reason to just study this case. We might as well lump them in any way we want, and then we called it superport. So this is actual real life. It's called multiport networks. You can find it somewhere in literature, but then everything I will say, you might as well study it in this much more general setting when you lump verticing boundary vertices together arbitrarily. Okay, so that's, yes?
What's the connection between this and multi-commodity flows where different substances flow through the same pipes, but you have conservation law for each of them? Like you are sending oil and water simultaneously, but they don't mix, and so there is conservation law separately for each of them.
This sounds very interesting, but I don't know if there's enough.
Yeah,
Some of the total current somewhere.
this, I suppose it would be a sum. I mean, this is well studied in network flow theory, like for
Okay.
Fulkerson style.
I'll consult my co-authors. Okay, I mean, it could be interesting. Anything else? So, and now the third very special case is the one Rick mentioned. So if, but when a superport has size 1, it just means the total current through the sink has to be 0, which makes it just an internal vertex. That's it. So that's, you can think of, usual electrical networks as everything is boundary, but with superports, but some of those have size 1, so they're internal. So this is the same as internal vertex. Okay, let me show you now a somewhat non-degenerate example of how this could look like. Example. So let's say we have the following electrical network, the following underlying graph. It has boundary vertices 1, 2, 3, 4, 5. 1, 2, 3 form a port. 4, 5 form a port. We'll choose 3 as a root for this one and 5 as a root for that one. And now we kind of play the same game. So what we are told, what is the boundary conditions here? We know the difference of potentials between 2 and 3, and we know the difference of potentials between 1 and 3. We also know the difference of potentials between 4 and 5. What we do not know, we don't know. Actually, there's no internal vertices, so there's nothing to ask about that. But we don't know the currents, right? So there's some current over here, I43, etc. And of course, we still need to know conductances. So let's say conductances of those edges look like this. Okay, so we know those differences of potentials. We know the conductances, and now we want to solve for resulting current. The theorem again is that there will be a solution and a unique one. And in this case, it will look something like this. If we set U5 to be 0, right, we can still globally shift all potentials by the same number, so we can make U5 to be 0. And then if you make Maple solve for it or some other software, it finds that U3, for example, is equal to this. 2, 3. Something like this, and then maybe, of course, potential at 4 will be just delta for 5 because we assumed this. And then once you know potentials and 3 and 4, you can, and you know conductance, you can find current, etc. So you can solve this whole thing just like we did before and find the answers. So let me write for you the response matrix in this case. How would the response matrix look like in this case? call it L. L plus B plus C plus D. And now we have a big matrix. AC plus AD. It's still symmetric. CD. AC. AC. AD minus AC plus BD. AC plus BC plus AD plus BD. So first of all, what are the rows and columns labeled here by? They're labeled by the boundary vertices which are not roots. Right? So they're labeled by boundary vertices. In our case, this is 1, 2, and 4. So 1, 2, 4, 1, 2, 4. And then the claim is that if you take this matrix and we decide what potentials we plant at 1, 2, and 4, let's see, does it sense? Or as sorry, not what potential, what's those difference, right? So there's a vector of 3 of those deltas, right? So if we multiply this vector of deltas by this matrix, it will give us a vector of incurrence into vertices 1, 2, and 4. Okay, so now what an interesting observation, or because slightly unfortunate, is that unlike previous case, there are polynomials here which have both plus and minus signs. Previously, it was not the case. So whatever formulas we could possibly have, there will have to be some rule for the sign. It will not be sign homogeneous. So let me tell you the generalizations of 2 theorems we had before. Right? I told you 2 theorems about the response matrix for the usual electrical networks. Let's see how it would look like in this case. So here's theorem number 1, which tells you what are the entries of this matrix. It says the entry Lij is equal to, in principle, it looks very similar. There's sum over some beasts in denominator, and denominator wouldn't even have a sign. And there's sum over something in the numerator, which will be weight of those somethings times the sign of this particular something, G. And now I need to tell you what those sums are over and how to determine the sign. So let me try. So F will be so-called, we call them valid forests, which means those forests that become tree if each port is glued together. Okay, so remember before that the denominator was sum over all forests such that each component has exactly one boundary vertex. Another way to think about it, the equivalent way, is that if you were to glue all those boundary vertices into one vertex, this would become a tree. Right? This would glue those components together. So now we are saying we're going to look for forests such that if you separately glue each of the ports together, it becomes a tree. So for example, over here, if you just pick edge A, and now we will glue those 3 vertices together, and those 2 vertices together, it obviously becomes a tree on those two vertices. So that's why we see this denominator A plus B plus C plus D. Okay, so far so good. And now what is the numerator here? So G's are forests valid with respect to I and J separately. which means what? So to be valid with respect to I means it becomes a tree, G becomes a tree if all vertices but I are glued to the root. Okay, so we do almost all the lumping we could do. We again glue each superport into one thing, except there's this one guy I who has his own superport. So everything else in the superport you glue together, but it's this one I just you don't glue it to anything. So it becomes a tree if all vertices, if all boundary vertices but I are glued to their root. Okay, so I don't have that much time, so I could tell you what the signs are, but maybe for the sake of time, let's just look at an example, and then I'll say a little bit more about, it's work in progress, and some things we figured out, but some of things we didn't. For example, of course, we didn't figure out full analog of Kenyon and Wilson theory of groves. But let's look at this example over here. Let's look at this entry. Why do we see AC minus AC plus BD here? Right? So L24 equals minus AC plus BD divided A plus B plus C plus D. So we are looking for force in this graph such that if we glue everything except for vertex 2 to the root, right? So we would be gluing 1 to 3, and we would be gluing 4 to 5, but we would leave 2 alone. Then I claim AC becomes a tree in the result. It seems true. And also AB. It doesn't, because it has to be simultaneously, it has to satisfy the same property for J as well. So let's take AB. So Rick's saying, so let's take AB. If we glue 1 to 3 and 4 to 5, AB also becomes a tree. But if we were to check it with respect to the other one, right, it's L24. We need to check 4 also. So now we glue 2 and 1 to 3, but we don't glue 4 to 5. Then, of course, AB would become a double edge, so it wouldn't be a tree. So anyway, so this filters it out, but then this is an interesting example because the sign will be different for those two, which doesn't happen in the normal case. So there's some rule for the sign, and you could also see what the rule is, and then it actually, there's similar formula for determinant of the whole response matrix. Let me not state it again, there will be some generalization. Let me just state for you some interesting open questions which sort of we think. So one open question is basically, is there something natural like this for other models? For example, there is a rather robust connection between just this very simple, vanilla version of electrical networks, the one I told you at the beginning, and simple random walks. So you could ask, what is a superport version of a simple random walk? So it seems like a very natural question. We don't know what the answer is. So that's the first. What is a superport version of, so first of all, simple random walk. You could ask Ising model. What is a superport version of Ising model? Here it's actually possible to make some nice guesses what it might look like. Also, just dimer model. What is a superport version of dimer model? Is there such thing? It will be very interesting. And another thing, so open question I want to show you is that in the case of usual electrical networks, there are those famous star triangle transformations, the local transformations, which preserves the response matrix, right? So, and this one, I think it's due to maybe Connolly. So this is very famous. What? Kennelly, yeah. So whenever you have a local piece of your electrical network somewhere inside which looks like this, and it has some weights ABC, you can transform it into a piece which looks like this, and then here you would plant ABC, and there's some precise formulas like something like, let's say A would be equal to BC, A plus B plus C, etc. In fact, we've seen those when I was writing the response matrix for this thing. If you carefully looked at what I wrote, you could see those formulas there. But you could ask, is there such similar thing, local moves? And in some sense, those moves are enough to connect any two networks with the same response. There's a theorem which says that any two networks within a class of planar networks with the same response matrix can be connected by essentially such moves and some simpler moves. So let me show you a very beautiful move found by one of my co-authors, Svetlana, for superport networks. It looks extremely similar to what this one looks like. And apparently, it also has the property that it preserves whatever one might want to preserve. So if we start with a network which looks like this, A, B, C, D, and we create two ports, this port and this port, it turns out that it's equivalent to having a different network, which now will look like this, A, B, C, D, with the same two ports, of course. And there are some precise formulas again, like A will be equal to AB, A plus B plus C plus D. And I can keep writing. So B equals BC over the same denominator, etc. So you can write explicit formulas. And this local transformation will have the property it will preserve response matrix, but also it will preserve the drop in potentials between the two ports. So I don't know if it was somehow clear in what I was saying, that you get to choose the drop on potentials within each port, right? So like potential here minus potential here, but you don't get to choose difference of potentials between two different ports. That's forced on you by the laws kind of nature. So even though this is not part of response matrix, you would also want those drops in potential between different ports to also be something preserved by local moves. Turns out that this thing preserves it. So is there a theory where you would say that any two networks with the same, like in a planar superport network, are connected by some list of local moves? This maybe would be one of them. That would be very beautiful if such thing existed. Okay, thank you so much.